I'm a seismologist by training, and today's talk will be about seismological observations. First of all, I would like to give a very quick 101 in seismic waves. In seismology, our primary wave field is composed from body waves and surface waves. As the name suggests, body waves mainly propagate within the matter, and surface waves are confined in the surface. They're interface waves. We use these kind of waves, we measure them, their amplitude, phase on a regular basis to understand the earthquakes or the source itself, and also infer the physical structure of the earth. The cartoon on the left is showing an earthquake in California, and on the surface a number of seismometers are placed, and as you can see, body waves or PNS waves are sampling through all the deeper part of the earth, and surface waves are confined in the surface. If you look at these wave fields, the seismograms itself, you will see they have a different travel time. Sorry.
You're seeing, we still see your first slide on.
Oh, really? Oh.
Just
how about now?
The share and starting again.
Oh, okay. That is.
Actually, it's on.
So I'll share it again then. Sorry. Okay, can you see my slides?
We see the second slide now. Maybe you can put in present mode.
Yeah, now I'm in the presentation mode.
Okay.
Can you see the second slide now?
We see still the first, but it's not in present mode.
Oh, okay, that's boring. And how about now?
The same.
Okay, all right.
Well, now we see the second slide.
Okay, all right. So that's not in the presentation mode. I think I will go through that. So it's just it will be a bit smaller, but it will hopefully will save time. Sorry about that. So I was talking about the seismic waves. These are we have primarily interested in body waves and surface waves. As the name suggests, body waves propagate within the matter, and surface waves are confined in the surface. They're mainly also called interface waves as well. In conventional seismology, we study these waves. We measure their travel time, amplitude, the phase, to simply understand the Earth itself. As you can see, body waves go through the deeper Earth. This is a hypothetical earthquake in California, measured at different sensors along the Earth, on the surface of the Earth, and surface waves are confined on the surface, and they tend to come later than the body waves. And if you look at a record section like that, you will see that they have different amplitudes and travel times, and also different waveform shapes. The nature of the source, this kind of waves, is primarily earthquakes, and that's very typical. Earthquakes itself creates, this top one is a seismogram, an example wave field. The initial part of the seismograms will have pretty deterministic wave fields. A good analogy will be like a droplet on the lake, where it creates concentric waves. But the later part is much more chaotic because Earth is heterogeneous, which creates loss of diffraction, conversion, attenuation, and you get a really long wave trains. Normally, it does not immediately make sense, but it is. We know that is a part of the earthquakes. Another important of the source is what we call seismic ambient noise. This has been known since the early days of the instrumentational seismology, but the nature of the vehicle is we just recently started to understand the details of it. In general, it's a very complex interaction of the atmosphere, ocean, and the ground, and that interaction creates elastic waves in a continuous manner, and we actually record these waves and also make inferences, which I will be talking about it. Now, I talk about the measuring and measuring the waves. We normally deploy seismic arrays. This is a conventional seismic sensor, which I won't be talking today, but normally in a seismic array, you will have hundreds or even thousands of them. And these are different examples from the whole global coverage, Australia, where those triangles are showing the coverage, and also much denser from USA. These instruments tend to be quite expensive, costing from several thousands to tens of thousands of dollars. And in general, they measure the velocity of the ground motion. Now, this is the conventional seismology. Pretty much in the last 50 years, we use this kind of instrumentation to measure the Earth's wave fields. But much recently, in the last 10 years, people show that actually fiber cables can be used as a seismic sensor, and I'll be talking about that. So this very simplistic example is showing how a light is propagating within a fiber example. As we know, this is mainly used for the telecommunication fibers where the information is transmitted. Most of the energy from this source is making to the other end, but there is always some backscattered energy. Now, this is nothing new because there is some imperfections within this sample, but the critical part is we can measure the location of this backscattering part. Now, at the same time, if there is some kind of perturbation in this one, then we will see that that location of that perturbation, the measurement point will be different, and then with some clever measurement methods, we can translate to some strain rates. And that's the whole idea behind using distributed acoustic sensing, which I will be talking in the next slides. So distributed acoustic sensing is, as I tried to say in my previous slides, is the biggest thing in seismology now. In the last 10 years, it's completely changing our understanding of the Earth. In simple terms, we are using a telecommunication fiber by repeatedly probing it with a laser pulse through an interrogator unit in this box on the top part, and that interrogate and measure the backscatter signal. If there is a source of perturbation, let's say seismic waves, that will be a shift, and this unit will can give us a strain rate at that point. The moment we know the strain rate, we can actually this cable becomes like a highly dense seismic sensor string. And we can use it to measure the Wavefield. In a typical setting, we can measure up to 100 kilometers along the fiber. So you can think that you put seismic sensors along this is 120 kilometers and recording it simultaneously. And because of this flexibility, we can repurpose all available fiber optic cables as a dense array of strain range sensors. Applications are not just in seismology, also ocean communities are starting to use it to understand some complex processes, and also smart city monitoring, from monitoring traffic to pedestrian traffic as well. As a part of this, since early 2021, we start to listen an unused telecommunication fiber starting from CSIRO campus in Kensington. By the way, we are in Perth. This is Western Australia, all the way to the Florida, another suburb. The cable is going through the city center as well, but the key thing is this is near real time, and it is equivalent to putting over 3,200 sensors on this string. So that's the extraordinary amount of density, which we can never get it in a conventional sensor technology. It is highly data intensive. You can get around a terabyte per day, but the great thing about it is real time, and we can do all sorts of things. Now, since we started this project, we start to look at some of the traffic patterns. Unfortunately, this was a video and I can't run it right now, but I can describe that. This is actually a 3-day period. You will see that starting from Friday early morning, and this is we are sensing this part of the cable, and we will see that because of the movement of the traffic, the amplitudes are quite large, and it simply dies down towards the night, and it picks up during Saturday, and Sunday continues. So these kind of cables are quite sensitive to the ground motion, not only for local activity, but an earthquake happened last year. 2 large earthquakes happening in New Zealand, roughly in northern part of New Zealand. This was a magnitude 7.3 event, and the separation was around 6,000 kilometers. We get clearly all these body waves that I previously mentioned, P waves, S waves, including some of the traffic noise. That's because that part of the cable is close to the city center. And this is an example. And another event happened again south of that earthquake. That was 8.1. Again, traffic noise dominated some parts of the cable, but we clearly get body waves, including some surface reverberations as well. Cable is not only picks up, that is offers a quite wide spectrum of measurements. This was filtered between 0.1 and 1 hertz. Even if you increase the frequency range to all the way to 1 to 2 hertz, we still don't lose the signal. This is pretty extraordinary. In a quite noisy environment, we can sense distant earthquakes. Now, that was obviously not the primary purpose of this work, because we want to do some structural imaging beneath the cable, and this is we are using this cable as a test bench. Now, I previously mentioned about some of the ambient seismic noise. Ambient seismic noise is quite useful, but it is not in itself, it is not very helpful to us. So what we used a framework correlation Wavefield. We take that ambient noise, we continuously cross-correlate between pairs of stations or sensors, and from that cross-correlation, we get an equivalent Green's function or impulse response of the Earth, as if we inject source in one end and listen to the other end, or other way around. Now, this has been used in seismology in the last 15 years with conventional sensors, and I can say it's completely transformed the whole seismology, because we don't have to rely anymore on earthquakes. We can simply look at differential measurements between station pairs, and as you can think, because it's between any station pairs, we get an excessive number of differential measurements. So in other words, if you have 10 stations, we will end up having 45 differential interferometric measurements. If we have 1,000, it will be close to 500,000. In our case, with over 3,200 sensors, we can get over 5.8 million interstation measurements, and that's very valuable, because the more data we have, we increase our subsurface images. Anyhow, so we apply this technique to this data set that we are currently getting from the PERT fiber. I'm only showing a portion of it because, as I said, we will have in theory over 5.7 million interstation measurements, which I can't show it properly. Instead, I'm just showing this section close to our campus. After cross-correlation, we clearly show that there are very clear Rayleigh wave propagation. Now, Rayleigh waves are very important in seismology because they are interface waves, and we use them to infer the subsurface structure, especially near surface, and we are getting completely from the noise correlations. Now, this was filtered quite high frequency, so the Rayleigh waves are very sensitive to the surface. Even if we change the filter range, we still get, for the same portion, we get the Rayleigh waves consistently. They arrive earlier because Earth gets faster in the deeper parts. And even at relatively low frequencies, the Rayleigh wave propagation is still very clear. If you look at some other parts of the cable, now I go much closer to the campus. At higher frequencies, some of the traffic noise creates some artifacts, but still we can trace the Rayleigh waves in both ends. So this is I forgot to mention that this is a diagram showing distance versus time, so we can easily figure out their apparent velocities. At another frequency, again, very coherent Rayleigh waves exist, and including even lower frequencies. Now, I'm from CSIRO, so I'm a part of the energy business unit. Our eventual goal is to use this technology to image the subsurface in a 4D manner. 4D means one of the, for example, in one of the key carbon reduction technology is to inject CO2 to the ground, but you have to monitor the evolution in real time. With this technology, we are proposing that we can actually do 4D measurements and map the dynamic changes from that Wavefield that I previously showed. Our smart cities, as a byproduct, we can monitor the traffic. We're already working on that. And not only we will be focusing on this cable, but also we will work on another cable in addition to the top one in PERT, and look at some inter-cable correlations as well. I thank you for your attention.
I'll open questions.